Hey, welcome back everybody. If you're watching this and you were part of the first semester I ever ran this course with this book, then I commend you for watching this because it's completely unrequired, but there's one more video for the final section of the book, which we barely weren't able to cover in our class. And really it's a nice conclusion chapter, and it's setting us up really well for PDEs if anybody wants to take a PDEs course. So we're gonna approach this from the fundamental relationship between ODEs and PDEs. And I'm starting again with this what I call map of differential equations, which I had placed in chapter 4, I think, maybe chapter 5. You'll have to look back. Look at that, 4.6. So in chapter 4.6, you can actually click on it in the book and it'll take you there. I referred to this map of differential equations where I was talking about how they're all related to each other and how maybe you move greater difficulty as you move down. But in fact, what we're going to see right now is, and something I think you've already seen, is we kind of trying to tackle this in the book so far, and we just saw with the Lie series that we actually send ourselves here, and actually we just saw with the method of characteristics that sometimes we send ourselves here, and actually using techniques from chapter 5 you can also send yourself here. So there's this path we take to infinite dimensional linear ODEs that we then solve with techniques from chapter 6. So that's really chapter 6. This is like part 3, the entire part 3 of the book. This is part 2 of the book. And then these finite dimensional linear PDEs is what you would tackle in a PDEs course, almost certainly. This infinite dimensional linear PDEs, you're already kind of pushing boundaries of things that mathematicians don't worry too much about. Like we're talking like infinite dimensional manifold theory. You're calculating geodesics on these infinite dimensional manifolds and some really crazy stuff. Maybe Banach space calculus. And same with like infinite dimensional nonlinear ODEs. You're starting to get into taking a finite dimensional nonlinear PDE, you can convert yourself to an infinite dimensional nonlinear ODE, and in fact you can start to push yourself up. And we're going to see at the end that we always try to push ourselves here because we have these chapter 6 techniques to handle these problems. But anyway, every time we move around in this map, things get tricky. So it's a very interesting way to perceive differential equations. And this is honestly just with like your traditional derivatives. So you can start to define very interesting differentials, such as like stochastic differentials, and differentials over discrete spaces, and so you can get into some really interesting stuff that even this map doesn't cover. But anyway, that's this map, and those paragraphs just kind of describe what I was saying in person for you then. But the point of this section is that transform methods, we're talking the Fourier and Laplace transforms that we've covered, and then we covered those in chapter 8 and 9. So chapters 8 and 9, when we had transform methods, Fourier series, the power series transform, these transform methods actually allow us to rewrite PDEs as infinite dimensional ODEs. Okay, and that's something that's kind of important here, because it means that when we have a linear PDE, we can reinterpret it as an infinite dimensional linear ODE. If we have a nonlinear PDE, we can reinterpret it as an infinite dimensional nonlinear ODE, and then start pushing ourselves around the map. And this all comes from the transform methods that we tackled in chapters 8 and 9. And so those are really going to be your gateway into PDEs if you decide to take a course there. I mean, chapter 6 comes into play certainly, but really you want to think chapter 8 and 9 is your gateway into PDEs. Also this chapter 14, where we just tackled the method of characteristics in the last section, that'll also be a good gateway, as well as what the following is, where I'm actually going to describe maybe how we do this with the transform methods. So we're going to tackle two PDEs that are somewhat easy but also ubiquitous. And we're going to tackle these, we're going to solve them in a somewhat general sense so that you can see maybe the beauty of using these transform methods. So the first PDE that we're going to look at here is the heat equation, and it's given by the following. We're going to take a derivative in time of phi, and that derivative in time is going to be equal to some constant alpha, which will be the heat conductance, which is the speed at which heat propagates through a material. And then we're going to have the Laplacian. And for those of you who maybe don't recall from Calc 3, the Laplacian is just the sum of the partial derivatives squared. So the sum of the second partial derivatives, partial squared, partial x, 2 squared plus dot 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 plus eventually you end up in your d-dimensional space, xd squared. So that's the Laplacian. And so we have one derivative in time on phi on the left-hand side, and we have a sum of second derivatives in space on phi on the right-hand side. And then, in fact, there is a forcing, some sort of external heat source, F, which is pushing heat into the system or pulling heat away from the system, dependent on time and dependent on where you are. You can imagine if I put a candle in the corner of the room, it's going to be hotter near the candle. There's going to be more heat pushed into the room near the candle, but it's going to fade over time. Eventually, the candle goes out, and then it's gone over time. And then there's also G, some initial heat source, right? So if I start standing in a room, the room has some initial heat and it's distributed around space. Okay, but that's the heat equation in a nutshell. Let's actually try to solve it. And actually, for solving this one, you aren't required to follow this remark, but I'm doing the remark just so that we can see both the Fourier series and the Fourier transform, how those might be implemented to convert ourselves to an infinite dimensional setting. So let's just assume, for example, that the functions f of t of x and g of x are periodic on the hyperinterval minus pi to the dth power. So in some sense, I'm working on some d-dimensional torus where everything is periodic. And so supposing that I have a heat equation evolving on some sort of periodic system, this isn't unheard of because the Earth is periodic in both dimensions, right? So if I move forward, around latitude lines or longitude lines, I'm periodic in both those dimensions, and so you can compute. You are periodic in multiple dimensions in a lot of cases. And what that allows me to do is calculate the Fourier series transform, right, or the Fourier series representations of f and g. Okay, so I'm gonna do this with an f and with a g, and I'm gonna compute their representations using f is b sub n, which evolves in time. So that's what's special about solving maybe these Cauchy problems in infinite dimensions, is that the variable on the left, which will almost always be time, you actually leave that variable inside of the coefficients. So the coefficients evolve over time. So the coefficients of my Fourier series are allowed to evolve over time. And that's true for f because f evolves over time. And then it's not necessarily true for g because g has no dependence on time. So for g, I have c sub n. Don't worry about its time too much. But what we get is we immediately get the solution from here. The solution to this heat equation is a Fourier series. So I have a Fourier series on phi, and it's a d-dimensional Fourier series. This is a slight generalization, and that's why I'm not assigning any homework problems from this because we haven't really talked about the d-dimensional Fourier series. But what I have is a d-dimensional Fourier series for phi, and the coefficients evolve like the following. So I take the coefficients from g, my initial heat distribution. Those coefficients exponentially decay at a rate of alpha. And then moreover, we can find the coefficients for f. Those kind of exponentially decay, but we've got a convolution going on here against the time varying coefficients of f, right? So b sub n are those time varying coefficients of f, and they're convolved with that exponential decay function, which this is actually a Gaussian function in n, but it's an exponential decay in time. And so that's where you can get the solution to this heat equation. And the way you actually prove it is by just assuming that phi can be written as a Fourier series in space, whose coefficients, once again, I'm allowing the coefficients to depend on time. So I allow the coefficients of my solution to depend on time. And upon allowing that to be true about the coefficients, if I rewrite the entire IVP, now this is really ugly when you rewrite it in its entirety, but this is the IVP. Right, it's the original IVP. If you jumped up to the top, you would see that. And if you rewrite it completely as Fourier series, and we just isolate the coefficients, right? Because the nice thing about Fourier series is that they're a group of linearly independent exponentials. So this is in some sense taking the Fourier series transform and just considering these as a collection of coefficients. If I truncate my system down to only those coefficients, the system looks like this. And now it's a relationship between coefficients. And this relationship is itself the relationship between Fourier series coefficients is an infinite dimensional ODE. Still an IVP, right? Still an initial value problem, but it's an ODE now because I only have one derivative right there on a sub n. Everything else is missing a derivative. And so I have an infinite dimensional case because there are infinitely many n's. But the nice thing here is that, in fact, since the Fourier basis diagonalizes the Laplacian, this is something really special about the Fourier basis. It diagonalizes derivatives. Since it diagonalizes it, I don't have any interaction terms. There's no a sub n plus 1, a sub n minus 1, a sub n plus 46 or something. There's no interaction between the a sub n's. And so we can really reinterpret this as infinitely many ODEs in one dimension, which are independent of one another, right? Each of these, when I fix an n, if I say n is 4, that ODE does not see the n equals 5 case. There's no n equals 5 showing up. And so you just solve each one of those independently, and we can solve them using theorem 7.3.2 because it's actually a one-dimensional linear ODE now, and it's pretty easy to solve them using theorem 7.3.2. It's really Duhamel's formula. But we go right ahead and you see that a sub n has to take this form, and we'll recall the whole point of finding a sub n was that those were the Fourier coefficients for phi. Okay, so then the Fourier coefficients for phi, they're time varying. They just go right in for the Fourier coefficients, and all of a sudden we've solved our PDE. This was actually Fourier's original impetus for finding the Fourier series, as he was trying to solve the heat equation in multiple dimensions, and this is what he came up with. So this is a really elegant way of solving the heat equation. So we can actually do something very similar with another PDE known as the wave equation. The wave equation has some differences from the heat equation. Most notably, we have two derivatives in time. And in many ways, this is the primary difference, but we change our parameter to, instead of alpha on the right, it's now c squared. This is just so it agrees with like the physics literature. So c describes the wave speed. So it turns out it's the root of whatever that parameter is, which describes the speed at which the waves propagate. And then we still have a forcing, but now we interpret this forcing as some external force of motion. Perhaps it's wind on the top of the water forcing the waves forward. And g of x is the initial distribution of the fluid. And unfortunately, because we're in two temporal dimensions, then our initial value problem, right? Initial value problems for each initial time, with each initial temporal derivative, we need, 1 minus the order of the IVP of conditions. So we have a second condition, which is actually the initial wave speed, or the initial velocity of the fluid, right? And that's what h is. And so this is what we get with the wave equation. And we're no longer going to assume we're periodic. We're not flowing periodic waves. We're going to flow infinitely large over an infinite amount of space. And in this sense, we take the Fourier transform of everything. And so this looks really, really complicated. It is slightly complicated, but we do have a nice solution. The solution is completely described by the following. It's you'll notice this is the inverse Fourier transform, because I have my e to the y x dy, and then I have my overall of space over here. The inverse Fourier transform of the Fourier transform of g against cosine in y. And then the Fourier transform of h over c norm of y against sine cty. And then I have this interesting behavior for the forcing f, where once again you can start to see this might arise out of Duhamel's, where I also have some cosines and sines on the Fourier transform of f. So it's a really, really big solution, but the fact that it fits on one line and we can solve the wave equation, which truly models wave in our external world, is not too bad, right? It does fit on one line, and this is the true solution. And the way we prove this is in a very similar manner, right? We're going to give ourselves we're going to compute the Fourier transform of phi only in space. Okay, so the Fourier transform of phi in space, if I transform the entire PDE, I get the following, right? Because we should recall from chapter 9, when we had the Fourier transform, the second derivatives become negative and then y squared. That'll be the second derivative. So the second derivatives in y become negative y squared. I'm just transforming f in space. I'm transforming phi in space. The time derivatives stick along for the ride. My initial conditions also transform in space. But what's nice here is that once again, since the Fourier series diagonalizes the Laplacian, this happens to be, if I parameterize each of these by the variable y, right? I'm just pretending like, okay, y exists, but I don't really worry about it, because if I look at these independent of y, this is just a one-dimensional ODE, and it's linear first order. And so I solved this one also with theorem 7.6.2, and in fact theorem 7.2.5, which 6.2 gives me the variation of parameters, which allows me to solve for the forcing. I solve it with those situations, and I exactly recover the Fourier transform of phi, right? Because what I'm solving for, if I solve this equation, is parameterized over y, I have a Fourier transform of phi, which depends on time, right? There's my temporal derivative t there, or temporal variable t there, and there, and then it's in the sine and the cosine. And so if I reinterpret that as a function of both t and y, I can inverse Fourier transform it and get my way back to phi. And so that's how we would maybe convert these two PDEs into infinite dimensional ODEs, right? In this case, that's an infinite dimensional ODE, in which case we can solve it. We can solve the infinite dimensional ODE. So this is the fundamental relationship between PDEs and ODEs. And this final remark is the final remark of the book, minus some appendices, where we really want to think about this pathway that everybody likes to take, unless we're just going to go ahead and use numerical approximation. If we want to get some more quantitative behavior, long-term behavior, other situational behavior of solutions to some really tricky problems, we often try to take this map. So we're going to take nonlinear PDEs and use transform methods on them, and that'll always give us an infinite dimensional nonlinear ODE, just like we were doing above, but imagine everything were nonlinear instead. We get something infinite dimensional and nonlinear. But the Lie series at the beginning of this chapter says, hey, I can reinterpret a nonlinear ODE as a linear PDE, and if I start in infinite dimensions, then I end in infinite dimensions. But now I'm sitting back into PDEs. So what we've done after 2 steps is go from nonlinear PDEs to infinite dimensional linear PDEs. But thankfully, accountable infinity squared is actually still accountable infinity. And so, in the right sense, okay, don't quote me on that, but in the right sense, if we end up using transform methods on this infinite dimensional linear PDE, we end up with an infinite dimensional linear ODE, and in fact, we do have solution methods from chapter 6 for these. So chapter 6 finally gives us some grasp of solution. But you can imagine each one of these transform methods really makes your problem pretty crazy. And the Lie series kind of makes it crazy. You're doing a transform method again. And so you can get into some pretty intense stuff, and there's a lot we still don't know about even linear PDEs. So I hope this gets you excited about ODEs, PDEs, chaos, numerical methods, dynamical systems, and all of it. And I hope you enjoyed the book. I'll see you in class. Bye.